Hello, chemistry. Here we are starting chapter 14, and chapter 14 is on acids and bases, as it says here. Acids and bases play a huge role in our lives, and we're going to talk about some of the common household things here in just a moment. But the big idea for this chapter is that acids are substances that can donate hydrogen ions in water. Bases are substances that accept hydrogen ions in water. So we'll talk a lot more about that. But first, let's talk about some common acids and bases. These are ones that you should know. And the first paragraph is on some common acids, and the second paragraph here is on some common bases. So some of the common acids are sour milk, rotten milk, and in there is lactic acid. This is also the acid that develops in your muscles when you overuse them. Vinegar, as we've talked before, is called acetic acid. Phosphoric acid, this is what is often used in soda, the colas and so forth. And that's phosphoric acid. It's kind of got a sour taste. We kind of like that. Most fruits, like lemons, oranges, grapefruits, they have in them citric acid. Apples have malic acid, and grape juice has tartaric acid. So I'd like you to know each of those different acids. Now, some common bases. A common one, and we actually often call it by this name, is ammonia. Another one is sodium hydroxide, NaOH. Its common name is called lye. That's often used in making soap and other things. And milk of magnesia is the common name for magnesium hydroxide. It's a suspension. It does not dissolve well. It's a very weak base, and so it's used as an antacid. That means you can ingest it and try to reduce the acid in your stomach. That's also what can be used for aluminum hydroxide and sodium hydrogen carbonate, baking soda. Often in antacids and even used in baking and so forth. So some common acids and bases that you should know. Now, what are some of the characteristics of acids? How can we know something's an acid? The big idea is still the main one, but let's get to some specific characteristics. First characteristic, they have a sour taste. So think of some things that are sour tasting. We just talked about some of those things such as lemons and soda and vinegar and apples and grapes and so forth. Those are sour, and so they fit in the category of acids. Now, something very, very important. Should we taste things just to see if they're acids or bases? And it says, taste should never be used as a test to evaluate whether any chemical substance is an acid. Why? Because some acids are very, very strong, like hydrochloric acid, and it will actually eat your tissues. So you do not want to taste it to see if it's an acid. However, if it's some food or something like that tastes sour, it probably is an acid. Acids also change the color of acid-base indicators. They're showing you here in this picture some paper, and we will do some things with some other indicators that, depending on how acidic something is, it will also affect the color that will be seen. So acids change the acid-base indicators. Some acids react with metals. What kind of metals? Active metals. So that's like group 1 metals, maybe group 2, to release hydrogen gas in the form of H2. You can watch on YouTube people doing some things perhaps that react this way, and one of the challenges is that it produces not only hydrogen gas but a lot of heat, and so if the hydrogen gas gets mixed with oxygen and enough energy, it can start to burn, and that would burn rapidly, and we call that an explosion. So this is not one of those try it at home things of mixing a strong acid with a active metal. You are very likely going to get an explosion, and when it explodes, if you have exploding acid going everywhere, you do not want that on you or other things. not to mention the container that it might be in, such as a glass container. Acids also conduct electric current. Why would acids conduct electric current? Well, from the last chapter we learned that acids and bases are electrolytes. That is, when they get into water, they will form ions, and those ions are what make it possible to carry a charge, and so they will conduct electric current. Now we're going to contrast these with the other characteristics of bases in your book. So bases on page 453 taste bitter. How do acids taste? They taste sour. So you've probably heard it talked about. Hopefully none of you have had experience to have your mouth washed out with soap because you have used some bad words. Well, how does soap taste? It is bitter. Many of the different foods that are bitter are basic. Another characteristic is that they change the color of an acid-base indicator. Well, notice it's what kind of indicator? Acid-base. These are bases, and so do acids change acid-base indicators. So both of them change acid-base indicators. Thirdly, bases feel slippery. Again, what you can know about soap is it tastes bitter, and is soap slippery? Yes. And in fact, when you're mixing up chemicals, like if you mix up some sodium hydroxide, you need to be very careful, because if you get any on your fingers and you're holding the container, it can get very slippery, just like soap, and you can slip right out of your hand. And soap wouldn't be too bad to have it break and make a mess. That'd be pretty easy to clean up. But this is sodium hydroxide, very strong, and it's corrosive and could be harmful. So acids will sometimes feel sort of slippery, but not like bases. Now, here it says the third characteristic, the active metals produce hydrogen gas. That is not what bases do. The contrast one is they feel slippery. Now, bases react with acids to produce salt and water. Well, that's just the exact converse of acids react with bases to produce salts and water. So one of the key things is here, what is made is a salt. Not always sodium chloride, but a salt. There are many different kinds of salts. So they produce salts and water. We've talked about that reaction many times before. And bases conduct electric current. Same reason why acids conduct electric current, because they're electrolytes. Now, there are strong electrolytes and weak electrolytes in acids and bases, so that's true, but they are electrolytes, so they will conduct electricity. If they do not form ions, then they're not acids or bases. So your textbook highlights some of the most famous acids, and there are 5 listed here. The first one is sulfuric acid, very strong acid, so common, it's the most commonly produced chemical, but yet so dangerous that many of you probably have never seen it, and it is difficult for you to buy. Kind of like at the store, they may ask you to be 18 to buy spray paint. They may ask you to do the same thing for something like sulfuric acid because it's dangerous. Its most famous known use by most people is in car batteries. So if you look at a car battery, you look at the top of the battery, and you'll see some warnings, skull and crossbones and things like that. That's because of the sulfuric acid that's in there that helps provide the electrolyte situation where the electricity can be transmitted. But it's actually not the most common uses. It's used in many things in industry, in oil refining, metal manufacturing, fertilizer, and many other processes. But the most famous that most people know is in car batteries. So you want to be careful with this sulfuric acid. It's also even used in a product we call Drano. Most often Drano is sodium hydroxide, but Drano also makes sulfuric acid Drano. And you can put it down the sink to dissolve hair and so forth to get your drain unplugged. So this is very serious, strong stuff. Burn holes in your clothes, eat your skin away. So you want to be careful with sulfuric acid. The next one is nitric acid. Nitric acid is also a very common acid. It's used in industry. It stains proteins yellow. So that means your skin and so forth is made out of protein. So if you get some nitric acid on your skin, it will turn yellowish brown for this reason that it stains proteins yellow. It can cause serious burns. It is used to make explosives. of nitrogen-containing compounds used to make plastic, dyes, medicines. And nitric acid is colorless, but when it's allowed to stand, it does decompose a little bit into nitrogen dioxide. This is the same stuff that comes out of the car's tailpipe that turns our air brown, especially in sunset time. We kind of makes nicer sunsets because it's brownish, and that's nitrogen dioxide, and that will turn the nitric acid a little bit brown. Now, one that you might be more interested in and like better is phosphoric acid, because the most well-known use is for putting in cola sodas. It's a flavoring agent in beverages. It also has a sour taste, but we kind of like this one. It's used for many things, including fertilizer and soap or laundry detergents, although we're getting away from that because it is also a fertilizer, and so it tends to make too much algae grow in our water when we put that into our laundry. It gets put into the sewer and then into the rivers and makes too much algae grow in the rivers. So it's used for many things like that. Hydrochloric acid, another very, very famous one. Some vocab words here that's kind of slip in here you need to know is if you were to go to the store and buy it, it is known as muriatic acid. So hydrochloric acid is known as muriatic acid. It's more well known or used in industry as for pickling iron and steel. It's used for cleaning all kinds of things, even put into swimming pools to get rid of contaminants. But if you go to the grocery store, or I should say a hardware store, you're going to want to ask for muriatic acid, otherwise they may not know what you're talking about. You can even use it to clean cement or etch cement. It's strong stuff. Now, it's also in your stomach. You use this in your stomach to digest your food. Very important, and it's kind of amazing. Wow, such a strong acid. It's in our body? Yes. You actually are digesting some of your stomach every day with the hydrochloric acid, and your body has to replace that. Acetic acid. Well, let's come back to this for just a second. Stomach acid, as you may recognize, when you have any bubbling up or you are sick and you vomit, in that burning sensation that you get in your throat and maybe in your nose, that is from the hydrochloric acid that is coming up, and your esophagus and those tissues are not used to it, and it's uncomfortable. It's also when you overeat and choose foods that don't digest so easily, such as meat and cheese and things like this. It can make the top of your stomach push some of the gases up into the esophagus, and that will start to burn, and we call that heartburn. If you have it too much, we start to call it acid reflux disease, and it's because of this hydrochloric acid coming up. How can you avoid that? Well, don't eat too much. Don't eat heavy foods that don't digest so easily, and you will not have much of a problem with acid reflux or heartburn. The last one in our textbook here is acetic acid. Another vocab word kind of sneaks in here, and that is glacial acetic acid. Pure acetic acid is colorless and a liquid known as glacial acetic acid because its freezing point is 17 degrees Celsius. Okay, that is room temperature typically is around 22 to 25 degrees Celsius, around 72 to 75 degrees Celsius. Fahrenheit. And that is just below that. So on a cool day, this acetic acid will actually turn into a solid. It looks just like ice. And so that's why it's often got the name glacial acetic acid when it's pure vinegar, as it will turn into a solid. Now, this vinegar you buy at the store is only 5%, so it will not turn into a solid because it's mostly water. Most vinegar, you buy at the store is 4 to 8%. And that concludes our primary acids and what you need to know about where we might use them. So just a little bit more on naming binary acids. The name is always going to start here with hydro. Then you can have the root name, which would be the name of the element with the "ide" on it. So instead of fluorine, it becomes fluoride. And when the acid is named, we take that "ide" and replace it with an "ic." So hydrogen fluoride becomes hydrofluoric. Hydrogen chloride becomes hydrochloric acid. And that's how we name the binary acids. The next category of acids is oxyacids. And as the name suggests, oxy means what must be there, some oxygen. Oxygen is a third element. So you've got hydrogen is your first one, and then you have some other element plus oxygen. So two that are always there are hydrogen and oxygen, and then somebody else. If you know your page R78, this one here, and you know your anions, then it's going to be very easy, much easier anyway, to name all your acids. Also, I provided for you this sheet here that you have in your handout. And on this paper, I broke it down into two categories. These are oxyacids whose names end in "ite." Nitrite, sulfite, chlorite, chlorite. This is hypochlorite. Now, notice that this says hypo, and these are all hydro. Some people get that confused. These are all hydro. Nobody else has hydro. This is hypo. As we learned before, that means it has one less oxygen than the "ite" anion. And so the naming becomes very easy. Notice that there's no hydro in front. You just keep the anion name, so nitrite. When it becomes an acid, becomes nitrous. So all the ites now end in "us." All the ates, phosphate, nitrate, sulfate, and all those ates, they're all going to end in "ic," which might be a little bit confusing because all the binary acids also end in "ic." But they all start with hydro, and these guys do not start with hydro. They just keep their anion name. So nitrate becomes nitric. And you can follow that pattern for naming, and we've done this all before, so it should be all review. So just a little bit about bases. Bases are so easy to name, they haven't even bothered to write the names here. You do need to know them, but it's pretty easy. All of these you'll see have OH at the end. We'll talk more about why they have OHs, but they all have OHs, and then you have the other element. So how would you name sodium with an OH? We call that sodium hydroxide. And how would you name KOH? Potassium hydroxide, rubidium hydroxide, cesium hydroxide, barium hydroxide, strontium hydroxide, and calcium hydroxide. Those are how we name the bases. And you do have to watch out for the group 2 elements. All are +2, so then you're going to need 2 hydroxides to balance that chemical formula, whereas all the group 1 elements only need to balance their +1 charge, and so there's one of them each. There are some weak bases. This is one that you need to know, and he's going to be a unique one. We'll talk more about it. This is ammonia. What's weird about him is that there's no OH, but when he reacts with water, he makes OH, and therefore that's why he's called a base, because he's increasing the hydroxide ion concentration. So it's a weak base, but it is one, and it produces hydroxide. Its name is ammonia. You need to know that. This one you do not need to know the name of.